You know,
of great magnitude.
Producing positive feedback loops, I think, is a kind of funny phrasing. The feedback loops are intrinsic to the system. And the question is, do we have positive feedback loops? And I don't think so. Not really serious ones.
Okay.
And yet they're assumed in order to get a big bang out of the CO2.
Yeah, okay, so on what basis are they assumed? Because you already made the case of degrees of freedom. So what's going on here scientifically? How can that story be put forward with any degree of credibility?
By saying it's credible. I mean, that's what we're doing. I mean, in other words, Suki Minabe did some papers in the early 70s where he assumed essentially one-dimensionality for the system, no clouds, no nothing. And he said, if I assume relative humidity remains fixed, and I have no clouds, or I don't let clouds change, then because of something called the Clausius-Clapeyron relation, the warmer it gets, the more moisture the atmosphere can hold. And if the relative humidity is fixed, you'll have more moisture. Okay, and he showed you could get a doubling of the effect of CO2 from that. It just happens to only apply in the tropics, and it is not, the clouds are not fixed. They are also changing and counteracting, I think, much of what's happening due to the water vapor, and changing the area over which the water vapor acts. So it's a much more complicated affair. And the measurements from satellites are suggesting that the whole shebang, when put together, is not producing the feedback that you needed to double the effect.
You've expressed a lot of skepticism about computer models. Now, when the average person reads that a computer model makes a given prediction, especially if it's reported in a peer-reviewed paper, they're inclined to presume that that means two things. It means data and it means fact. But I'm very skeptical of computer models because you have to make all sorts of assumptions, and the devil's in the details with something as complex as climate. So on what grounds have you gone after the climate models?
Well, actually, I have a use for the models. There's no way that models can accurately, well, there is a way maybe, simulate fluids. I mean, the trouble is our atmosphere, our ocean, have motions on every scale. They have motions on the scale of your fingernail. They have motions on the scale of the planet. They all have an impact. The small-scale turbulence in the boundary layer, the clouds, which have a scale of a kilometer or so, the weather patterns that have scales of thousands of kilometers, and you're modeling them on a computer. And even today's massive computers can't resolve a centimeter. That would be incredible. So they have to assume what the small-scale turbulence does. They have to assume what the clouds do. They have to assume what, all sorts of things are doing. And even then, there are some systems where you can prove mathematically that as you reduce the mesh size over which you're approximating things, because you're not doing it continuously, you have to just make points, that it converges to the right answer. But no one has ever done that for fluid dynamics. We don't know if it even converges. So you have to, in these models, put in, often you'll run a model and it goes haywire. You throw in damping to prevent it from going haywire. The damping has no physical basis. It's just to keep the model from blowing up. You're doing all these things, and you're hopeful that it may still have some insight. Now, I said,
Right.
I actually am not against models. So, for instance, if you do theory for a phenomenon in the atmosphere, you usually do what's called order of magnitude analysis. What that means is you take the full equations and you try to estimate how big and small the terms are. And you try to see if these terms are small, can I approximate the system with a simpler system? And can I test it in this way? And you learn a lot from that. Almost everything we know came from that sort of analysis, not from models. But once in a while, if things get complicated, I'd like to look at a model and see whether there were things possibly going on in the model that might go on in nature that I hadn't thought about. And so the models can be useful promoters of more thinking about possibilities.
Sure. Of course. That's very different than assuming that they're valid models of what's going to happen with the real climate.
And
so, okay, I have two questions on that front. Is it hard to approximate fluid dynamics regardless of mesh size because a fluid system has so many degrees of freedom?
It's very hard to do. I mean, nobody would pretend. Let's say you have a gurgling brook with pebbles and so on, and it's doing all sorts of things. Nobody's going to predict the eddy for, let's say, a mile. I mean, that would be hopeless. You might make a statistical forecast on certain things, and you might get useful information, and you might be able to make an approximation that tells you how the roughness of the surface affected the flow rate and so on. But and you know, all you do is scale that up many orders of magnitude, and you have the Earth's atmosphere, and those little eddies that you couldn't track are now your weather systems and so on. You still have trouble tracking them.
Well, so part of the issue here is that we're dealing with temperature changes that are of relatively small magnitude compared to the potential range of temperature change. And what that means is that for that degree of accuracy in prediction, let's say you need an accuracy of 1 to 3 degrees over 100 years, you have to have an unbelievably finely tuned model at an extremely high level of resolution. And then with the difficulties in modeling fluid dynamics, it isn't even obvious that you could do it in principle.
I think that's probably true. You can restrict, as I say, you damp the models, you keep them from blowing up, you do all sorts of things. And, for instance, with the greenhouse picture, I've been critical of it because I think it only really is useful in the tropics. But it is useful if I'm comparing Venus and Mars and Mercury. For them, the gross idea of the greenhouse does tell you why they're different. But, the changes in the Earth's climate involve minuscule temperature changes compared to the temperature differences between the planets.
Right. Well, then we have the additional problem on the political front so imagine you have an unstable climate model or an inaccurate climate model at the scale of resolution we're discussing. And then you put on top of that an economic model. And the economic model uses the climate model as an axiom, and then it tries to predict out 100 years, which I just don't see that as going anywhere at all, because you can't predict economic development with any degree of accuracy over a 100-year period. If you could do that, you'd have all the money in the world almost immediately if you could generate a model that accurate. You simply can't do it.
No.
So if you stack a bad economic model on a flawed climate model, you really do have a Tower of Babel.
Well, and they don't even do that. I mean, the economic models that people like Nordhaus and so on use just take that metric for climate and assign...
Right, but they assume it's accurate.
And they assume that you can put a monetary value on it.
Yeah.
And then, tune the... I mean, there are various kinds of models that do these things, but I don't know what to say. I mean, I don't think any longer that it is the models that are driving the perception. I think it is the pure repetition. And this was understood from the beginning. In 1980, when Jim Hansen gave testimony to the Senate about finding that there was global warming. And Newsweek had a cover. And the cover showed the Earth on fire and had the label, "All scientists agree."
Right, right.
Now, you had all sorts of funny problems at that time. Like most weathermen disagreed. And the American Meteorological Society decided they needed re-education. I mean, the march through the institutions was pretty effective. And we could talk about that. I mean, that's been